These toys dazzle with their color and the patterns formed. To create their beautiful displays, all rely on the formation of drops. Droplets, especially controlling the size of droplets, is of enormous technological importance. The mist from an asthma inhaler, the paint sprayed on cars, or the fuel entering the cylinder of a car's engine. To understand how engineers control drop size, let's start with this toy. It clearly shows the essentials of drop formation. A narrow stream of liquid called a jet flows from the opening and then becomes circular as it flows toward the bottom of the toy. This circle breaks off to form a droplet. As you can see here, the droplets are typically the same size. This toy motivates the key scientific question. Why does a droplet form at all? Why doesn't a jet go on forever without breaking up? To answer that question, I've put a small hole in this cup and filled it with a 50-50 mixture of Valium by water and glycerol dyed green. Glycerin is highly viscous, meaning informally that it's a thick liquid, so it slows the flow and the formation of droplets. You see a smooth jet exits, but as it travels farther from the cup, the stream gets fuzzy, which you can see if I zoom in. Let's slow this to see what occurs. You see the smooth jet at the top. Then, as the stream descends, droplets forming, the fuzziness earlier. Notice that just as the liquid exits, it forms a uniform cylinder, but as it descends, the cylinder's sides wobble and bulges form and disappear until this instability slices the jet into drops. The instability is caused by a liquid's tendency to minimize its surface area, a tendency toward the most thermodynamically stable state. For this jetting liquid, that would be a sphere rather than a cylinder. The surface area to volume ratio of a sphere is double that of an optimized cylinder with the same radius. The instability forms quickly. Look at the liquid exiting the cup. I said it was uniform, but you can now see that the wobbling begins soon after exiting. The flickering is the wobble, seen better if I zoom in and add guidelines. Why, though, doesn't the cylindrical jet immediately become a sphere? That's because the minimization of the surface area competes with another tendency, inertia. To see that, look at one of the bulges that forms and disappears. These are, of course, failed attempts by the liquid to form a sphere. Notice what must happen for a sphere, a droplet, to form. Some liquid must travel in the opposite direction of the stream's flow, but this flow is opposed by inertia, as defined by Newton's first law. An object at rest stays at rest, and an object in motion stays in motion with the same speed and in the same direction unless acted on by an unbalanced force. So the flowing liquid keeps flowing downward, pulled by gravity, until the minimization of surface area forces some liquid to move up, creating these bulges. Upward flow occurs because at the ends of the bulge, where the stream is constricted, the pressure is higher than in the middle, so liquid flows toward the middle. Although these bulges are large here, recall that wobbling near the top. Each wobble moves a bit of liquid up, increasing as the stream descends, until eventually, as we see at the bottom of the stream, the surface area wins and droplets form. The wobble observed at the top of the stream suggests how engineers can create precisely sized drops. To create a stream with uniform drops that appear immediately, we need to vibrate the stream at a frequency near that of the wobble. Watch the stream again. Notice that the drops form near the bottom of the screen. Near the cup, no drops form. But if I repeatedly tap the side of the cup, drops form soon after the stream exits the cup. Here's a clever engineering application of this method to produce drops. It's the inkjet printers used to code packaging. On the bottom of the almond can is a sell-by date, on the ibuprofen an expiration date, under the cap of the soda a code used perhaps in a contest, and on this cleaner a serial number. These codes were printed by industrial-strength inkjet printers that throw ink up to an inch as products move by at speeds up to 2,000 feet per second. These industrial printers, known as continuous inkjets or CIJs, create precision droplets using tapping to break a jet into droplets. Ink from a reservoir is pumped through a nozzle. The nozzle sprays a jet of ink onto a surface, a box or a carton. The jet's so powerful that the printer can print in any direction, from the top as I showed earlier, or horizontally as shown here. The letters or images created are composed of dots of ink. To generate these droplets, an oscillator plate, a piezoelectric crystal, vibrates the nozzle. This is akin to tapping the cup to break a jet into droplets. I show on the stream breaking into uniform droplets, but in practice some small droplets called satellites also form. To select the right size droplets, the droplets are charged by electrodes and pass through high voltage plates. The larger droplets are more highly charged, so they deflect more than the smaller droplets. These satellites are collected and recycled into the ink supply. The droplets stop and start as needed. And to create the letters, some printers move the nozzle, others change the voltage to redirect the stream, and some printers have multiple nozzles. These commercial inkjet printers are only one example of the technological importance of creating precisely sized drops, but it illustrates how all technological applications that use droplets rely on the minimization of surface area as the driving force to form a droplet. I'm Bill Hammack, the Engineer Guy.